what happened is that you try to find out the eigenvalue of this gamma. So suppose it is 2 by 2. So you will have two eigenvalues, lambda 1 and lambda 2, and then the explosive root you will have to get rid of. Okay? Otherwise, you will end up with explosive solution because we are looking for stable solution, right? So you have to somehow, if you find that those lambda, which is bigger than 1, you have to take care of it. So how do you take care of it? So here you need to find out the eigenvalue. So the gamma, find out the eigenvalue. So here, let's say, suppose your A matrix like that, right? Okay. So the definition of eigenvalue is that you want to find out this lambda, right? So this lambda x. So here you should have lambda 1 and lambda 2, and the corresponding x1 and x2 vector, they satisfy this kind of relationship. So you will end up with something like this. So here you have like x11, x21 times the lambda 1, and then you would for the 2 by 2 case, A is known, right? So given a matrix A, and you are supposed to find lambda 1 and lambda 2, and also these two vector, okay, that satisfy this relationship. Okay, so this vector, and then this is known as the eigenvector, and then this is eigenvalue, right? Eigenvalue and eigenvector. Okay, and for simple cases, we know how to do it. Okay, so for the 2 by 2 case, you need to solve a quadratic equation. Okay, so for example, like because for 2 by 2 case, we know this kind of results. The determinant of A is the product of the eigenvalue. Okay, and then the trace of A, the sum of the diagonal element, is the sum of the eigenvalue. Okay, lambda 1 and lambda 2. So here, let's say, so the determinant of A, we know how to do it. Okay, like this, right? Cross product. And then the trace of A is the sum of the diagonal element, A11 plus A22. Okay, so here actually this you can, so this is lambda 1 and lambda 2, right? So here you can replace, let's say you can express lambda 1 as this, lambda 2 substitute into the second equation, so you will have a quadratic equation. So you should be able to find that is something like, so the solution would be something like, I guess, I don't know, let's see, see if you I believe it would be something like this. I don't remember, but let's see. You substitute. Okay, substitute into the would be something like this, right? You got this trace of A, and then you multiply throughout by lambda 2, trace of A, lambda 2, and then this will be a quadratic equations, trace of A, lambda 2 plus this one, right? Quadratic equation, we know how to solve this, right? We have formula for this one, right? High school. So this lambda 2 will be the trace of A plus and minus trace of A square minus 4 times the determinant, and then divided by 2, right? Okay, so we have formula, and we know how to calculate trace of A, right? A11 plus A22, and then this thing, so that formula we can do it, right? Without any problem. And then the eigenvalue, you can find it out, right? Suppose you have already found out lambda 1 and lambda 2. Okay, suppose you have already found out lambda 1 and lambda 2, then you can do let's say x1, x2. Suppose you want to have, suppose this lambda 1, you apply the formula, you already know. So this one is lambda 1 and lambda 2 because it's plus and minus here. So then just by definition of the eigenvalue, you just take any, you need to take one row and then you can solve out and do a normalization. Moreover, you need a normalization because the definition of eigenvalue is ax times lambda x, therefore you can multiply x. So it's non-unique, right? Because this cancellation. So you need to apply a normalization rule, like divide everything by the norm of the x or set the first element to be 1 or whatever, right? So basically we know this can be done, right? At least for the 2x2 case, you can even do it in pencil and paper, right? And for higher dimensional case, computer, right? Without any problem. So basically, so we know these things can be done, although may not be easy by pencil and paper, but most most cases we need to rely on the computer. Okay, but conceptually this is straightforward, right? So if we have computer, we should be able to do it. For numerical solution, no problem. So here we find out. So you put all the eigenvalue on this lambda matrix, and those x1 and x2, right? So this is the eigenvector matrix. So you have this object, and by definitions, this is your original matrix. You find out all the eigenvector, you put them into P, and then put the eigenvalue on the diagonal element of lambda. So you have, so for the 2x2 case, you got something like this. So let's say this is, so this lambda would be something like this, lambda 1, lambda 2, right? Would be like this. Right? And then the P would be the two, let's say P1 and P2, two column, right? Okay. And then P inverse, just take the inverse of this P. Okay. And then by you can check by definitions, AP would be P lambda, would be P, let's see, AP would be P lambda, yeah. AP would be P lambda, okay. So it will satisfy this relationship, and then of course you can multiply, post-multiply by the P inverse, you will get this, okay. So this is just the definition, follow from the definition of, so AP1 equals to lambda 1 P1, AP2 equals to lambda 2 P2, okay. So just like that. So you will get this, and in the lecture notes, A is gamma, right? So let me just keep the same notation. So this gamma things, and then you will have this original system. So we try to decouple the dynamics. So how do we do that? So it's gamma xt minus 1 plus other terms, right? Okay. And because this gamma is p lambda p inverse. So let me just substitute in p lambda p inverse xt minus 1 other terms, okay? And you can, on both sides, you can calculate P inverse, right? Multiply by P inverse. So let's copy back this gamma xt minus 1 on the top. And this will be P. Okay? And then you multiply throughout by P inverse. So you so you multiply throughout, and then you just call this thing WT, and this will be WT minus 1, right? Okay. And obviously this is just I, so you end up with something like a transform system. That looks like that. Okay? Like this. But remember though, so this W1T, W2T, lambda 1, lambda 2, W1T minus 1, W2T minus 1, and then plus other stuff. And so you will end up with after this transformation, you will end up something like this. Now, then you can check the size of lambda 1 and lambda 2. If for the lambda smaller than 1, no problem. It will give you a stable solution. So here you will have, so you will see in this case, so if you look at the first row, because this lambda 1 times 0, right? So you multiply, you end up with two equations. Lambda 1t equals to lambda, this W1t lambda 1, W1t minus 1 plus other terms, right? And then you will have W2t lambda 2 plus other terms, right? And then you can just check this lambda 1 and lambda 2 one by one, okay? Now, whenever you see the lambda that is bigger than 1, you want to, then the only stable solution is everything is 0. Okay? Suppose your lambda 2 is bigger than 1. Anything non-zero, because you will sort of recursively would becomes explosive. Okay, so the only stable solution for, so let's suppose lambda 2 is bigger than 1. Okay, suppose lambda 1 is smaller than 1, then no problem. You don't need to do anything. Lambda 2 bigger than 1, then the only solution is everything 0. So you need to impose these conditions. So here, this is what is explained in this lecture notes by Ludwig. Okay, so this basically this case. So let's say you look at the two equation case, and this is your P. Okay, so this is your P. So this is a column, first column, second column, and then this is the first row of P inverse, second row of P inverse, lambda 1 and lambda 2, and then you multiply throughout by P inverse, and this should be up there, and then you kind of define this to be WT. So basically you want to transform, let's say your original XT is actually CT and KT, but then you multiply by this matrix. This is a linear combination of CT and KT maybe. W1t equal to 1/2 CT plus 1/2 KT, whatever, right? Some linear combination. And you will end up with these diagonal things here, the diagonal matrix lambda 1, lambda 2 on the diagonal. And then for each equation, you end up with something like this. And then you can check this lambda j now. Is it bigger than 1 or smaller than 1? Smaller than 1, no problem. Bigger than 1, what happened is that, suppose this is 2, okay? Suppose this is 2, then if your initial value is not 0, if this part is also not 0, suppose this is 1, okay? Suppose this is 1, suppose this is, maybe for simplicity, suppose all this thing is 0. You got a 1 here, you multiply by 2. Next time you have a 2, and then you feed it back here, 2 times 2 is 4, and so on. So it must be infinity eventually, right? So, or similarly, suppose this is, so let's say the initial W is 0, but this part is not 0. You will find that eventually you will be explosive. So the only stable solution, whenever you have this lambda bigger than 1, the only stable solution is to have the initial W to be 0, and also all these terms, this whole bunch of things must be 0. Okay? So this is the way you can get rid of explosive behavior. Okay? So basically what happened is something like this. So here, suppose you use this notation, whenever the lambda is bigger than 1, you call them unstable part, right? So the part that is unstable, indicated by this U, and the part that has a lambda smaller than 1, you call them the stable part, indicated by S. So in your system, the stable part, you don't need to do anything about it. So just keep it there, okay? Keep it, so this one, because this one is smaller than 1, okay? Just keep it, right? For the unstable part, you will just add this 0 there. Originally, you have the lambda U, right? You have the lambda U, but then because the lambda U is bigger than 1, so you want to have a system that will exhibit stable behavior. So this is how we get rid of the explosive part. Okay? So by construction, this system will be stable. So this is what people call you get rid of the explosive root. Okay, so you have one stable root, one explosive root. The stable root, no problem. You want to keep it. Okay, so the explosive root, you want to set all these things to 0. And then you do the reverse transformation, right? Because your original variable is the xt, right? CTKT. So how do you get the W, right? So you multiply your xt by P inverse. So you want to reverse this transformation, right? So you multiply by P throughout. Then you will recover your original variable, right? So you multiply by P. Everything, so P here, P here, P here, right? Okay, so you will recover the original variable. Like that, okay? And this will be the stable solution. This is the stable solution. So this the computer will try to solve that. And yeah, there's a point. Now where's the forecast error. So you will see here, this is the stable solution, but then where's the eta t? There's a CT now, but where's the eta t? So the eta t will be taken care of in this step. So this part, see the unstable part, we want to set this to 0, right? Set this to 0, okay? We want to set this to 0. But this is actually very useful. Okay, so the unstable part, you set this thing to 0. So you can try to solve eta t in terms of ZT. Just use this relationship to solve out eta t and then substitute out. Okay, and here let's think of the simplest case. Suppose in our 2x2 system, you only have lambda 2 bigger than 1, right? So this thing should be one-dimensional, right? So this is a one equation, basically a one single equation. And then suppose you have one eta, okay? Suppose you have one eta, then presumably everything is 1 by 1, and as long as this thing is not 0, you should be able to solve it, right? So something like eta t equals to this object divided by pj times pi, right? Okay. So here the solution of this eta t in terms of CT will actually determine whether the stable solution will be unique or does not exist, or is it has many solutions. So for example, in my handwritten example, I actually have 2 eta, right? The ET, because I have the ET-CT plus 1 and ET-ZT plus 1, right? So by this principle, I should have 2 eta. Now, if I only have one unstable root, can I solve out eta t uniquely? Let's say this is one-dimensional, right? Because pj dot is the eigenvector correspond to the unstable root, right? Okay. So if you have only one, let's say, suppose now I need to go beyond 2 dimension, right? Because I have 2 eta. So let's say you have a 3 equation system. You have lambda 1, lambda 2, lambda 3. Okay. Suppose only lambda 3 is bigger than 1. Lambda 1 and lambda 2 is smaller than 1. But I have 2 eta. So then there should not be a unique solution of my 2 eta, right? There should be infinitely many solutions, right? Okay. So in this case, actually there will be infinitely many stable solutions. So this is actually of interest in macroeconomics. This is known as the indeterminacy case. Okay, so in monetary policy, so maybe in the new Keynesian model, I guess we will talk about the Taylor rule. So it turns out that if the Taylor principle is not satisfied, if the central bank is not aggressive enough to raise the interest rate when there's inflation, the equilibrium could have infinitely many solutions. So you could end up with a case just like you have too few explosive roots, okay? Too few explosive roots. So, but for the moment, you can, by looking at this linear equation system, right? Because this is a linear equation system, you can count the number of equations and the number of unknowns, right? So you treat the eta t, how many eta t's are there? Okay, so a very simple way to kind of check the number of solutions is that you must have the same number of explosive roots compared with the number of eta. But the number of eta is the same as the number of your conditional expectation term, right? Because we said that the principle, right? Whenever you see a conditional expectation, just get rid of it by introducing an eta. Right? So this is known as the Blanchard and Kahn condition. It's a famous condition in this field. So you need to have in order to have a solution, you need to have at least as many. So the explosive root, you need to have sufficient number of explosive root. So it is not true that explosive root is bad. It may be a good thing, okay? So because it will ensure your solution. So in the 2x2 case, of course, there's not much possibility, okay? So in the 2x2 case, if you have one eta, you need one root, right? So one explosive root. If you have two eta, then you need two, right? Okay. So this is known as the Sims method, and then this classical results. Amazingly, so when I work on my PhD thesis, I asked Professor Sims, and he said he gave me a C program or these things. Yeah, he told me that he worked on that for 10 years. I make use of his results, but I didn't in my PhD dissertation, and then 10 years later he published it. It becomes a classics. So if I was clever enough, I pick it up, then maybe I got my name in it. But just genius. I mean, just Nobel Prize guy. It's amazing. So these things. So this insight, I guess this insight is unique. So this method, there's the precursor of this method is known as the Blanchard and Kine methods in the ABC book. So you sort of talk about the Blanchard and Kine method. It's a classical method published in 1980. And then what Sims add to it is this insight, this simple trick. Whenever you see a conditional expectation, you add a eta t. See, when you look at the algebra, it's trivial, right? This is how you get Nobel Prize. I mean, these guys are just trivial thing. Nobody think of trivial thing, and then he can think of it, get Nobel Prize, right? He deserves it. So it looks like trivial, but so far nobody think about it that way. And also, I guess another very useful result is that this concept of multiple solution, unique solution, and so on. Okay, by looking at this system, okay, so you can actually look at, because in linear algebra we have theorem on under what condition your linear system will have a solution. Under what condition there must be a infinitely many solutions. It's not new. You look up linear algebra textbook, it is there. So basically you just apply those theorems, and then you can establish results under what conditions this thing will have a unique solution of eta t in terms of the set t. Under what condition there's no solution, under what condition that infinitely many solutions. And then Thomas Lubick was clever enough when he worked with Professor Sims, he picked it up. So Thomas Lubick worked with him in Yale University after me, and he picked up these things and published a paper working on apply this concept to monetary policy, the sunspot equilibrium, and so on. So it's like gold mine, right? So when you go to go to the class of smart person, don't fall asleep, right? So just listen to something, you pick it up, and then you will get a nice result. I failed to do that, so that's why I'm here. Okay. Just pick it up, right? So he gave me the program, but I don't know how. I just apply it in some way, and then because back at that time, maybe it's still under developing. He didn't got the idea, he didn't got the answer, and still work on it. But if you count the time, so they published the paper in 2002, but okay, I worked in 90 something, so this So I think that at least this thing has been, you work on it for 20 years or something like that. So it's hard to imagine you work on a problem for 20 years and you're not tired or sick and tired or something like that. So it's just amazing. Anyway, this is now is the sort of classic results. So this phi is the solution. So because let's say suppose you have you can solve, right? So suppose you have the same number of exclusive roots, then you can solve eta t in terms of zt. So eta t will be phi times zt. So you substitute out. So this is how you get rid of this eta t when you transform back to the original variable. So these 5 things, right? So they substitute out. So as you can see from this handout, okay. So this is the final solution. So nowadays is standard things in software. Even Stata, the latest version of Stata, start to have these things. So use the Sims method. Okay. Okay, so we are running out of time today, and I try to work out the example for you. So we will now in your homework, you need the MATLAB or Octave, right? So you can free download Octave from the website, right? From you Google search, and then you can free download without any problem. And I have tried it, so it really works quite nice. So it's just the same. Any program that you write in MATLAB can be run in Octave without any problem. Okay, so go to Octave website, just download. It's free download. It is exactly the same